All right, everybody. So the readings for today's lecture, it's still that Sage handbook reading. And as I've mentioned last week, I think it's a good one, pretty thorough, a little bit dense, but hopefully it'll help. I've also assigned a blog post from the Data Colada blog. This is a blog run by Yuri Simonson and Mike Nelson, and Joe Simmons. If those names sound familiar to you, they wrote this article about hacking. It's called False Positive Psychology. They update this blog semi-regularly, and I think they write really clearly. They have one on a particular issue that we'll touch on in today's lecture that has to do with logistic regression. It's a fairly brief blog post. I expect it would take you maybe 5-10 minutes reading. It's pretty short, but I think it's pretty clear. So I recommend that you, well, it's assigned, but I recommend that you actually do that reading too. A couple announcements. So first of all, we put out a course evaluation on, I think it was like Thursday that the link went live. I forgot to mention that we were doing that last Wednesday. So I'd just like to encourage you to actually do that. It's important for two reasons, although of course you're not required to do the course evaluation in the slightest, but it's important to me for two reasons. One, because I take this feedback seriously. I hope that's something that you've been able to see a couple times last semester. You know, I really do listen, even if I don't do exactly what every suggestion is. I try to think about it and incorporate changes. So I'd like to continue to do that. I want this to be a good course for you. The second reason is that we have these class days that are right now on the schedule. And I've already used some of them to do the philosophy of science unit. And I'd like some input about what other topics you'd like me to cover. So I'm open to covering a wide variety of topics. There are a couple that I'd be a bit more prepared to cover. So I've taught a class on meta-analysis, for example. If you're interested in meta-analysis, that's how to aggregate findings across papers in a quantitative way. So we have a lot of materials on that. And so usually experience with meta-analysis, a lot of my research involves meta-analysis. So another one that I'd be prepared to do right off the bat is something about missing data. Another one that I'd be pretty prepared to do would be something on like data wrangling, data management, how to do that in R, and how to think about how to like future-proof your analyses so that you have to keep that at a minimum. So a couple people have expressed interest in that topic. I'd certainly be reasonably prepared to teach it. Although if you have other interests and you want me to spend a day or two or 3 or 4 on one of these topics, please do give your input on the survey, otherwise I won't know. So next Wednesday, of course, is going to be our first in-class exam. And it's going to follow a similar format as the in-class exams last semester. As I started to do last semester, I'm going to give you a study guide. Something that's new this semester is I understand that you all, or a group of you anyway, used a Google Doc to take notes collaboratively when you were studying. So I'd like to make that official. So I'm going to include a link to that Google Doc when I give the study guide on Wednesday. So if you want to make use of those collaborative notes, go for it. Right, and then lastly, with regard to the take-home that you just turned in, I will get the key back to you before the in-class, so that again, that feedback. I'm not sure. We'll see how long it takes to do the actual grading. I'm going to do my best to get it to you to get the specific feedback to you in a prompt way, but I'm just not sure. So we'll see. I'll do my best. and hopefully I can get all that to you before the end of the week. Questions on it? So we're continuing on with this unit on generalized linear models. And today we're going to go through a couple, iterations, extensions of this special case of the generalized linear model called logistic regression, which is what we've been, working on since last Monday. Just to give you this ahead of time, this is going to be the last, or my last planned day for logistic regression. So this is it. And my intention all along wasn't necessarily to go through every case that you could use logistic regression. Instead, I'm trying to give you some principles and that you can use to, suit your research scenario should you have to use this technique. And I'm trying to tell you some of the places where logistic regression differs from regular regression. So that's the emphasis. So I'm going to try to give you a couple different cases to help you see the principles in action. But my intention was never to go through everything. I'm going to go through a couple things, and hopefully that gets you the basic idea. And I'm obviously also giving you some resources that you can use if you have to use this technique on your own. Also on Wednesday, we're still going to be covering the generalized linear model, but we're going to be covering another case, or in sort of broad brushstrokes, we have a couple other cases where you could use the generalized linear model. So I'll show you how to extend some of these principles. I'd like to focus on this example that I introduced back on Wednesday. So we've got a dichotomous independent variable, predictor variable, whether or not someone went to a top-ranked school. And we're still trying to use that to understand the probability of admission. And I went through this case very rapidly back on Wednesday. So there were a couple things that I didn't have quite enough time to point out that I want to show you about this specific case. So on Wednesday, I talked about how, just as we did with the general linear model, you can replace these text labels with some arbitrary numbers, like -0.5, +0.5, and then just go through the same basic process that you go through to fit any logistic regression. So you find those estimates that maximize the likelihood function, likelihood being, that the probability of observing these data given a particular hypothesis. So you find the estimate that maximizes the likelihood. And in this particular case, you get a prediction line that corresponds to those maximum likelihood estimates that looks kind of like this. One thing that I didn't say explicitly on Wednesday is that there are a couple of points on this prediction line that correspond to proportions that you can get out from just like looking at a cross tabulation of admissions and rating. So this up here is just the number of people who, at the top left corner, that's the people who went to a low-ranked school who were not admitted. There were 245 of those people. Below that 94, those are people who went to a low-ranked school but were admitted. Top right, top-ranked school were not admitted, and then the 33 is top-ranked school and were admitted. So this is just like basic cross-tabulation table. I've shown you tables like this when we went through various different kinds of categorical analyses. So I'm just doing the same thing here. Well, as I said, it turns out that there are certain points along this prediction line that correspond to calculations that you can do using this cross tabulation. So I can calculate certain proportions using this cross tabulation to obtain numbers or statistics that you can pick out on this graph. So think for a minute, what is one thing that I can calculate from this table that might be represented somewhere on this graph? And just to orient you, of course, this y-axis is the probability of admission.
Could you take the number in each cell and then divide it by the total number?
Yeah, so I can do some division, and that'll get me something that's represented on this graph. Can you be a little bit more specific? So what calculation, what numbers could I divide by what in order to get something that's on the graph? Or anybody else if you have an idea? Yeah.
Where the red line crosses the lower ranked dotted line, that one would just be the 94 divided by the sum of 94 and 245. So it'd be the whole group of lower ranked people, and then that calculation would be the proportion probability.
Right, exactly. So in order to see that, remember this is the probability of admission. And right here, this is this vertical line represents our the lower ranked schools, minus a half that we gave those lower ranked schools. So where this dotted line crosses the red line, that ought to be a predicted probability of admissions among lower ranked schools. If I want to calculate that, what would I do? Well, I take among the lower ranked schools, the number of people who were admitted, and then divide by the total number of people from lower ranked schools. So that would be 94 divided by 94 plus 45. Everybody follow that?
So that number tells you what?
That's the proportion of people among lower ranked schools who are admitted. Or another way of thinking about that is that it's a probability of admissions for people in lower ranked schools. Okay. So there ought to be something else that I can calculate from this table that might be represented on the graph. You could calculate.
You do the same thing for the higher ranked schools, and then maybe subtract those. Any difference in probability?
Well, let's go with the first thing before we think about comparing this to. So what specific calculation would I do to get the probability for higher ranked schools?
I think it would be the same as you said for last year, 33 divided by 28 plus 33.
Absolutely. So this is the other major point on the x-axis where we have, data. Positive 0.5, which represents higher ranked schools. Where this dotted line crosses the red line, that gives me a predicted probability for people in higher ranked schools. If I want to calculate that, one thing I can do is I could take 33 divided by 33 plus 21.
Patrick, I'm not sure if this is a stupid question or not, but
It's not a stupid question.
okay. Can you explain to me maybe why we're doing 94 divided by the other ones instead of 245 divided by the total?
Sure. So admissions is, we have zeros for people who are not admitted and ones for people who are admitted. In order to find the probability, a probability of admission, you have to have the number of people who are admitted over the total. If we're just looking among lower ranked schools, we look in the first column instead of the second column. So in order to get that probability, we take the number of people who are admitted in lower ranked schools, which is 94, divided by the total, which is 94 plus 245. Does that clarify things?
Yeah, what if you wanted to know the probability of not being admitted? Then you do the opposite.
Yes. So you take the number of people who were not admitted over the total, and then plus something. Does that clarify things? So this should give you, sorry, did I talk about
You could say you could also do 1 minus that probability.
Oh, yeah. Absolutely, absolutely. So this can anchor you or give you another feel for what it is that we're doing when we're doing logistic regression. We're finding predicted probabilities. And in this case where we have two groups, we have two predicted probabilities, which we can get from this cross-stat tabulation table. Does anybody remember one way that we could represent this sort of dichotomous design when we were working with the general linear model? So it turned out that dichotomous designs where you have, let's say you're looking at top rank versus bottom rank schools, but you're looking at generic schools. Turned out if you did an analysis with top ranked versus bottom ranked schools as the predictor, and GRE scores as the outcome, that was an analysis of a particular kind. You could represent that analysis in kind of an interesting way. Does anybody remember what it was? We made tables, but tables of what? Means. So this ought to give you another anchor as to like, okay, so we're still looking at particular statistics that we can calculate on our own, right? In our models, representing them in a particular way. So we still have that like representation of a table of something. That was true with the general linear model, that's true here. What's changed is the particular statistic that our model is representing. So before it was a table of means, now it's a table of probabilities or proportions. Does that make sense? Yeah.
It's not related to that, but why do you have like a comma before the C on that table and not a bar code? Just curious.
Oh, this is you've used select before. So this is an alternative way of selecting particular columns in a data set.
Okay.
This is called bracket notation. You can think about like accessing an Excel spreadsheet. The stuff before the comma would be the columns or the rows that you want. The stuff after the comma is the columns. So I'm trying to access all the rows. That's why I just put the comma and nothing else.
Okay.
And the columns that are called admit and top underscore weight. Right, so I drew that entire prediction line just to show you that you can get predictions at any point that you want on ranking. But really, the two things that we're comparing are this proportion and this proportion, or this probability and this probability. That's what the model is fit to understand. So with that in mind, that should give you another anchor point for understanding this output. So this right here is what you get from the GLM function. Actually, before I do that, this 1.12, that's testing the difference between low-ranked and top-ranked schools, but transformed into log odds. So it's not a direct test of those proportions that we were just talking about. Instead, it's the test of a transformation of the proportions. It's that thing called a logit. This right here, it's also a test of the difference between those two proportions. But again, it's not directly the proportions, instead it's a transformation of the proportions. So this right here is a ratio of odds. It's the odds of admission when you're at a top rank school over the odds of admission when you're at a bottom rank school. So one way of understanding what that's telling you is that your odds of admission increase threefold if you're at a top rank school versus if you're at a bottom rank school. One thing that's important here is that you think of this in terms of multiplying the odds of the lower rank school by some number. So this tells you by what numbers you have to multiply the odds at the lower rank school in order to obtain the odds at another rank school. Yeah.
So something that is not lining up here with the drill we talked about a little bit, it seemed like the odds coefficient was said to be a decrease in the odds.
Right, so if odds ratios go from, from 0 to whatever. So if that odds ratio were below 1, that would indicate the odds are decreasing. You have to multiply the odds of admission in a top rank school by half, which decreases the odds. So this right here will never be negative. Instead, numbers below 1 indicate decreasing odds, and numbers above 1 indicate increasing odds.
I think in the drill, the estimate was like negative something, and the odds ratio was positive.
Right, so this right here, the log odds, that can be negative. But when we go to odds, we exponentiate log odds. Odds can never be negative. Instead, when this is negative, this will be a number less than 1.
So it's less than 1 and the odds decreasing as you move to that next variable.
Correct.
Greater than 1, odds increase.
Yes. Again, it's multiplicative, and that's why you have to think about when numbers less than 1 indicating decreasing odds. You multiply some number by a number less than 1, that number gets equal. So I mentioned this a couple times in a couple different ways. One thing that's important here is that these are both like different ways of understanding the same thing. You're still comparing these predicted probabilities, but using different metrics. One is in the log odds universe, the log odds kingdom, whatever you want to call it. The other one is in the Gauss universe. There's not a one nice number that does that comparison in the probability universe. It's much easier to think. I prefer odds ratios, and that's usually what you see when you see papers that use logistic regression. Because it still has this relatively intuitive interpretation, but it is slightly removed from the probabilities.
Gotcha.
Yeah.
You would likely cover this, but so when you're doing like a write-up on the interpretation of that, what do you say? You say the odds are increasing by 3 units?
I'd say the odds increase threefold if you're from a top rank school versus a bottom rank school. And I would also give the specific probabilities. So those numbers that those numbers that are at the top half of the screen. Because the odds ratio doesn't care where you're starting. It could be that you're going from 1% to 3%. not super impressive. But going from 28% to 54% is a little more impressive. Yeah.
Then so if you were decreasing, you would say odds are decreasing by whatever number.
I'd say people from, say, lower rank schools have 1/3 the odds of admission as people from top rank schools. I have a couple examples later on of interpretation, and then before I head into that other case of the generalized linear model, well, sometime on this anyway, I'll give you a sample right up in a graph.
Stats too.
Yeah.
So they're not actually logarithmic numbers, right? Like the log odds numbers? Like,
Yeah.
So, like, because when you exponentiate at well, I'm confused because if you do like e to the like log of 1.12, it should just be 1.12, right? So that's what like.
E to the 1.12, so e is what, 2.71? Did I get that right? I think it's 2.71. So 2.71 to the 1.12 power will be just slightly bigger than 2.71.
So it's not e to the log of that number. It's
e to that number.
Okay. So. Okay, I got confused because. Okay.
I think you got it. It's e to this number. And then in order to get from here to here, you take the log of this.
It's just like the name log odds, and then I'm thinking, oh, the log parentheses that number, but that makes no sense, right? Like it's.
Yeah, so it does make sense because this is the odds right here, and then you take the log of this log parentheses, and that gives you this. Other questions? Okay, let's make this slightly more complicated. So now instead of just comparing top ranked schools to everybody, we're going to be comparing top ranked schools, middle ranked schools, and bottom ranked schools. So we've added another level to this variable. And we're still trying to understand the same outcome. The hypothesis that we're working with is people from top ranked schools will be admitted with a higher probability than either people with at middle ranked schools or bottom ranked schools. But we're indifferent about the comparison between middle and bottom ranked. So a little bit of review. What sort of coding scheme do you think represents this hypothesis?
We use dummy code, right?
Dummy code, and so.
It's going to be 1, 0, 0, or it could be reverse 0, 1, 1.
So the reference group is the group that always gets a 0. And what's our reference group in this case?
Or top ranking.
Okay, great. The top ranking is the reference group. So what does that mean in terms of the actual numbers?
It'll be 0, 1, 1 for the contrast 1. Contrast 2 will be 0, 0, 1.
Absolutely. Great. 0, 1, 0, 0, 0, 1. This is the coding scheme that we're working with. Here's what the data look like. So I'm starting with those text labels. I haven't replaced them with numbers yet. I'm adding some color coding. That's going to matter later on. But for now, all I've done is put these in different colors. Before I get to actually fitting the model, I wanted to do a quick sidetrack. So I just mentioned a little bit earlier about how in this two-level case, you can think of each level as being represented by a portion. So given that information, let's one number that you can calculate from this table that might be represented somewhere on this graph? Just give me one number.
So it's gonna be the same as the last graph, where you can do like 33 divided by 28 plus 33.
Absolutely.
3 times.
Yep. Perfect. Absolutely. So before we could think about this graph as representing 2 different proportions. Now we can pick out 3 different proportions. So here are those proportions. And of course, the way those are calculated is by taking, say, 33, the bottom row, over 33 plus 38. And you just do that 3 times. So it's one extra layer of complication. We're now thinking about 3 different numbers instead of 2. And our coding scheme, of course, gives us different ways of contrasting these proportions. So I've changed the outcome variable. Right now, I'm just showing you the process that we went through when I showed you I developed this 3-level case with a quantitative outcome. So when we're working in the general linear model, here's what we do. We have this like color coding thing, and we created a coding scheme that divides up our 3-level variable into 2 mechanical variables. And then what we could do is create a plot for, say, the first mechanical variable. So I'll just put C1 on this x-axis. And in order to account for the fact that C2 is also in the model, we had to do this adjustment process. Specifically, what it meant to adjust for C2 was to subtract out its effect. And literally what we did is move up those spread points by an amount dictated by the value of C2. So that's review. That's what we did in order to work with dummy codes when we had a quantitative outcome. Well, let's see if we could follow that same process with a dichotomous outcome. So here's that color coding that I showed you just a moment before. Here's my coding scheme. Now I put C1 on this x-axis. Here's what happens when you put C1 on that x-axis. So now I've basically moved the points that representing the people at bottom rank schools over to 0. And the people in the middle rank schools are over at 1. So now we have to do that adjustment process, right? So before we subtracted out the value of C2, but we're kind of in a quandary because it's not really clear how we subtract out the value of C2. We're working with these 0s and 1s, right? So what does it even mean to subtract out a partial value for, you end up with numbers like 0.3 or numbers that aren't 0 or 1. It just doesn't make sense. So we encountered a similar problem when we first learned how to do logistic regressions. You know, it doesn't make sense to talk about someone getting a value within 0 and 1. That's one of the reasons we moved to logistic regression and ended up, figuring out maximum likelihood estimation and all this other stuff. So it was a problem before, and it's a problem here too. People following why this is an issue? Basically, we're encountering another situation where the methods that we were using before just don't quite work in a straightforward way. Well, before, when we encountered this problem, we ended up moving to this log out space, this subgrid a separate area where we could work with numbers other than 0 and 1. We worked with log odds. And of course, that's why we had to, maximize the likelihood instead of minimizing the sum squared errors. So that's going to save us here too. So what I end up doing is I move to this log odd space, and I lose my data points. So just as before, I can't talk about like adjusting data points. Instead, I'm still doing the adjustment process, but what I'm adjusting is my predicted log odds as opposed to the data points, then using those new data points to minimize the sum squared errors. So we still have this disjunct where in the log odd space, my zeros and ones don't really exist. That's true here too. But we're still doing an adjustment. The adjustment just looks a little bit different. So this line right here represents what happens if I ignore the fact that I have C2 in the model. This is my predicted log odds without C2. But just as you could, like, when you're maximizing the likelihood, we work with both a slope and an intercept. Well, we can also work with extra variables that we add to the model. So that process looks the same. You still like jiggle around the various values of C1 and C2 in order to find the ones that maximize the likelihood. You're still doing that same process. You just have an extra variable to do that with. And that gets you a different slope. One that's different from what you get if you just included C1. So similar process, you're still like finding the values of certain parameters that are best according to some criterion, but best here means maximizing likelihood. And if you have another variable in the model, the maximum likelihood estimates are going to be different than if you excluded that variable from the model. Questions?
Yeah. So you're probably gonna kind of explain this for me, like math, how that works. There.
I'm not going to go through the math in detail, but the process looks kind of similar to what we did back on Wednesday. So on Wednesday, you write out this function that allows you to calculate the likelihood. It's a product of different probabilities. And then that function should calculate that probability based on some parameter estimates. So when we just had one variable, we had two parameters, a slope and an intercept. Now we have two slopes and one intercept. But we're still writing out that function that allows you to calculate the likelihood based on some values of those parameters. You then vary those parameters systematically. That's literally what happens under the hood when you call GLM. It goes through that iteration, so it has a specific way of varying the parameters. And it calculates the likelihood each time, and then it picks out those set of parameters that maximize the likelihood. You're maximizing a conditional probability. So conditional probability is given that if we accept that these are the values that we're working with, our coefficients, what's the probability of observing our data given those coefficients?
I get that. Sorry for taking this time, but
That's good.
I'm trying to reconcile it with the contrast thing that we did.
Mm-hmm.
Accounting for that C2.
Yep.
Just trying to understand.
Yeah, well, that's what's tricky, right? Because we can't actually see what's happening to the data because we lost the data. We're in the log hospitals. So before we had that kind of intuitive way of seeing what it means to control for C2. We sort of subtract the same number from all the points that are in the bottom right group. Now we don't have that intuitive way of understanding what's happening. That's still basically what's happening under the hood. But there's not like a clear way of visualizing it because we're in the log hospitals.
Great news.
I guess my question is, just a little confused. So are you like, when you're subtracting out C2, is that because you're trying to subtract out the effect of the bottom right?
You're trying to, yeah, sort of. You're trying to estimate the comparison between top ranked and middle ranked, holding constants or controlling for the comparison between top rank and bottom rank. So one way of understanding what that means is you kind of subtract out the comparison between top rank and bottom rank. From the points that are in the third group.
So you're just controlling for the relationship between top and bottom right?
Yes.
Okay.
And so can you go to the most recent? Here. This one, it seems that it adjusted up so much more. Is that because of the weight that the bottom rank schools hold in that relationship? There's more of them.
One way to understand what's happening here is that if I don't control for C2, this is contrasting middle rank to the average of top and bottom. I want to take out that average of top and bottom, so that's just top without thinking about bottom. So to do that, you control for the second contrast, which sort of subtracts out the effect of the bottom rank schools. We don't have a way of seeing what's happening to the points because the points are just 0 and 1, but that's one way to understand what's happening.
I'd be curious to see if we set the bottom rank to the reference group, to how much that adjusted line would shift.
Yeah, I don't know. It would look different. Of course, whatever's the reference group is the thing that you're always comparing to the off group.
I'm just trying to understand in my brain what the the density of the dots are kind of saying. This was a graphs.
Yeah. So the dots that are in green are points that I don't want them to have anything to do with my focal comparison, right? That's the thing that I've set to 0, but it's not the reference group. So I don't want those to factor into my estimate of the comparison of the black points and the red points. That's why I have to control for the second contrast. That's what that does. It makes it so that we can interpret this contrast as only the comparison between top and middle. So in some ways, these green points right here, they're points that we don't want to consider. And by setting up the contrast in this way, we ensure that they are considered. Does that make sense?
Yeah, I get that. I was just a different question, but we can continue.
Okay.
So what's like the math behind when you say you're controlling for contrast to make a comparison between top rank and middle rank? Like, what is that math like? I'm confused about that.
You write out a thing called the likelihood function that calculates the probability of observing these data given a certain hypothesis. Your hypothesis is, that the intercept, the coefficient for C1 and the coefficient for C2 all take on some value, an arbitrary value. You change those values of the parameter systematically and calculate those conditional probabilities a bunch of times. There's going to be some set of coefficients that produce the maximum likelihood that maximize that conditional probability. Those are the ones that you end up with. So I guess if you want to know like the nitty-gritty math, look at the stage handbook. It gives a couple examples. That's what's happening conceptually. What ends up happening is you're multiplying out a bunch of probabilities every time you maximally calculate that with a big problem. And you end up with a very small number. That's why it's nice to work with the log likelihood instead of the actual likelihood. I'm glad that you're asking these questions about like what's actually happening here, because that is the kind of understanding that I want you to have. Obviously, we can do this with C1. We can also go through this process with C2. So in order to find the best parameter estimate for C2, we have to somehow account for the effect of C1. To do that, we have to go to the log odd space. And if you do the math, you'll end up with some coefficient for C2 that's very different from the one for C1. Or then for C2 that's very different than if you didn't make that adjustment process.
Are these the actual adjustment lines? Or are these just
lines that are in there? I think I copied over the wrong image because it says C1 on the x-axis. So I'll replace that. But anyway, you can go through this similar adjustment process. Once you have those maximum likelihood estimates in log odd space, you can use these bridges, these mathematical bridges, to figure out what the best fitting lines look like in the probability space. And you end up with curves that look kind of like this. And you can do that with both C1 and C2. Essentially the same process, or a very similar process of adjustment happens with generalized linear models. This happened with the general linear model, but we lose those data points and we end up maximizing the likelihood instead of minimizing some square roots. So here's what our maximum likelihood estimates are. Here's a graph in probability space. In order to figure out what these estimates are telling us, of course, we run into that problem, right, that the thing that we're actually interested in is in probability space, but these coefficients are given in the log odd space. But you can still look at these coefficients and they, obviously you can like do those transformations to go to odd space that maybe makes a little more sense. But I wanted to give you a couple anchor points for understanding these estimates just as they're given on your own. So obviously one interpretation of that 0.16, the intercept, is students from top grade schools have 0.16 log odds of admission. But log odds of admission, I mean, what does that even mean? Well, log odds go from minus infinity to positive infinity, with 0 meaning 50-50 odds, or a 50% probability. So one way of like just very quickly understanding what that 0.16 means is that people from top ranked schools have approximately slightly better than a 50-50 shot of getting it. You can, of course, use this exponentiation function e to whatever in order to go from log odds to odds. And that gets you this 1.18 value right here. And what that tells you is that people from top ranked schools, 0 of both my predictors, have about slightly better than 1-to-1 odds of being admitted. So similar to what we learned from looking at the 0.16. Probabilities are often easier to think about than log odds or odds. So one way that you can get those probabilities is you fit a model that you're going to use to make these predictions, and then you use the predict function. When you tell it type equals response, you're telling it, give me those probabilities, so give me log odds. And it gives you the 0.54. That's that 54% probability. And that's the thing that we can tie back to this graph in probability space. Notice the 0.54 is, that's our estimate for top ranked schools. It's just above the 0.5. All right. Let's try the minus 0.75. So in terms of log odds, can someone tell me in a sentence what that minus 0.75 means?
Yeah. Change in log odds from top to middle rank schools controlling for bottom rank schools.
So it means that people in middle rank schools have 0.75 log odds, less of a chance of getting into graphic school than people with top rank schools. Quick way of understanding what that's telling you, just think about how log odds work. In general, negative log odds indicate decreasing probabilities or decreasing log odds technically. And a coefficient of 0 would mean no change. Coefficient, a positive coefficient would mean increasing log odds. We can, of course, take e to that power to find the odds. So this right here is an odds ratio. It tells you by what power or by what number do you have to multiply one odds to get to another odds. Anybody want to take a shot at describing in a sentence what that 0.47 means? So we give you a hint. Yeah, go ahead.
I was just going to say, I think it's the odds of admission for a middle ranked school student is 0.471, so it'd be approximately 1 out of 3.
Yeah, so we're always making a comparison to the top ranked school. That that number's about 0.5. That means that people at middle rank schools have about half the odds of getting admitted as people from high rank schools. So you think about multiplying the reference group by that number, multiplying what you're starting with by that number. So you have to see where you are. So again, you get to use that in a sentence. You could say people at middle grade schools have about half the odds of admission as people at top grade schools.
In a write-up, if you wanted to be more precise, would you say students in a middle grade school have 0.47 the odds of admission compared to people in higher grade school?
Yeah. You talk about decreased by a factor of. That's a good term phrase. So decreased by a factor of 0.47, or if it's a number of 1, increased by a factor of 2.
Just say 47, 100.
Sure. Absolutely. Whatever's clear, I like using that increased by a factor of, decreased by a factor of. I find that's easier to think about, relatively easy to think about. Of course, if you want to get the underlying probabilities, the things that you're probably most interested in, you can use predict to get those. There's that 0.54 probability and the 0.36 probability. And those are the things that you can actually point out on this graph. So if I drew a vertical line at the 0 point, the blue line would meet the vertical line at 0.54, and right here, the vertical line would meet the blue line at 0.36. So this is a new graph, that second graph that plots C2 on the x-axis. Can anybody use that coefficient in the sentence to describe what's happening in our model? How would you interpret that in the sentence?
That's the log odds.
Mm-hmm.
So the graph says done. And this one we're comparing top and bottom, right?
Correct.
So you're controlling the middle, okay.
Oh, yeah, sorry, typo. This should say middle rank. I'll fix that.
So the log odds of getting admitted into grad school for a bottom ranked school, negative 1.47, a factor of negative 1.47 less odds, log odds. I don't know.
You can just say the log odds of admission decreased by 1 point, whatever that is, 1.47.
For bottom ranked schools compared to top ranked schools.
Yeah, or you can say the log odds of admission are 1.47 log odds lower for bottom ranked schools compared to top ranked schools.
In all honesty, would you ever write it up? Okay, that sounds insane.
It is insane.
Yeah.
Log odds are very hard to think about.
Yeah.
I guess I have seen them reported sometimes, but I much prefer odds.
Right.
Odds are probabilities.
Yeah.
So I would pretty much always work with the odds. But this is what the model gives you, and this is what the model is working on. So it does help to have some understanding of what that means.
Quick question.
Yes.
So, for our stats sort of write-up, when we're looking at odds, what statistics are we using? Are we using that ANOVA output when saying whether an odd difference is significant or not?
For significance tests, yeah, use that ANOVA output.
For the odds.
That ANOVA output applies to odds, log odds, and probabilities. Those are significance tests for everything. These quantities are not quite the same because they're transformations of each other, but like in terms of how statistics work, they are the same. We're doing this little mathematical trick to solve some problems that occur in the probability space that don't occur in the log odds space.
Gotcha. But the p-value are just a little bit different.
Correct. So the likelihood ratio test is more powerful than the test that you get from the default output. That's why I recommend the likelihood ratio test. I would pretty much always go with those two values. If you want to know more about significance testing, there's some discussion of that in the reading assigned for this unit. There's also a supplemental reading I posted today that talks about that. Right, so students from the bottom ranked schools have 1.47 log odds, lower the chance of getting admitted than people at the bottom ranked schools. This is the odds ratio. Someone take a stab at describing in a sentence what this odds ratio means.
So the odds of getting into a
Incorrect.
graduate school decreases by a factor of 0.23 for people who came from bottom ranked schools compared to top ranked schools.
Yeah, exactly. So compared to people at top ranked schools, people at bottom ranked schools have about a quarter of the odds of getting them. And of course, as before, we can use predict to get the actual probabilities. And those are the things that are actually represented on this graph, which is plotted in probability space. So this is the 0.54, this is the 0.21. Those probabilities or ratios are, those are the things that are, we're working with 3 different ratios of probabilities. Those are the things that bring the most. So another way of understanding this coefficient is that the probability being admitted is 0.54 for people at top grade schools and 0.21 for people at bottom grade schools. So of course we can understand all of this in terms of this table right here. The table that I brought up at the beginning of this particular problem. So thinking about that intercept, how can I use that table to get a number that helps me understand what that intercept means?
Is there the probability of not being admitted to graduate school for someone who came from a top ranked school?
It's still the probability of being admitted. So that this is always the probability of being admitted. But yes, it is for someone at a top ranked school. And what sort of calculation would I do to get that probability?
You would do the, 33 over 33 plus 54 plus 40. 33 over 33 plus 28.
So we're always looking at people at top ranked schools, the 1 ranking. So
So 33 over 33 plus 20.
absolutely.
Wait,
That's
that's not the.
that's the probability. Outputs and log
Oh,
odds.
oh, okay.
Right. So the output is in log odds. The thing that the model's working with is log odds. But we can still understand what's being represented by that log odds using this table. So we have this disconnect. The unfortunate disconnect that we've always been working with this second model. And that,
Wait, why is the intercept still the probability of them being admitted for a top of the school? I guess that was my question. You think is being admitted is represented by 1 and not being admitted is represented by 0?
correct. I could have made not being admitted 1 and being admitted 0 if I wanted to. That would tell me the probability of not being admitted.
Right.
It's a little bit arbitrary.
But I guess I was confused because I thought the intercept is when everything is equal to 0.
We're
But I
working with
guess
dummy
it's just the
coding.
predictor.
We're working with dummy coding, so at 0 on both my predictors, it is top rank schools.
Okay, I think where I was confused is because now our outcome variable is 0 and 1s, and so I was thinking that everything had to be
Yeah.
equal to 0.
This is a little bit confusing, for sure.
Wait, so you're saying log of 0.54 should be 416?
You have to translate that 0.54 into odds. So
that over 1 minus, oh no, that over that minus 1.
odds would be that over 1 plus 0.446. And then you take the log of that to get back to here. You always have to travel both of these bridges to get back from probability to log odds. Okay. What about this minus 7.75? How can I understand that minus 0.75 in terms of this table?
The log odds are the difference of the probabilities between top and middle rank schools, right?
Right, so I'm absolutely. So what's one quantity that I can calculate from this table to represent what's being compared?
Probabilities for each and then.
Yeah. So one quantity is I could take 33 over 33 plus 38. That's what I was working with before with the intercept. The other one is I could take, say, 54 over 54 plus 97. So I'm comparing the top ranked schools to the middle ranked schools. That's how I calculate the probability of admission for middle ranked schools. That minus 0.75 is comparing those two probabilities.
So if you do the 0.54 minus 0.36 and take the log of that, it'll be.
It's not the difference. Remember, the things that, so these log odds are the things that you can add and subtract. You can't even add and subtract probabilities. You have to you have to go to odds. Odds get multiplied together. Then if you go from odds to log odds, those are the things that get added and subtracted.
So that's the difference in log odds.
Correct.
Those two probabilities.
Correct. This is what complications talk about that was not bridges. You can't just add and subtract these probabilities. Instead, you have to travel to the log odds space. Those are the things that can be added and subtracted. That's why you work with that odds ratio, that thing that you multiply together instead of something that you add together. So odds are multiplied.
That's minor type there, on the 38.
Oh, yeah. Thank you. I'll fix that as well. So those are the two probabilities that are represented on the graph. But of course, they're not the things that our model's working on. Our model's trying to understand log odds. All right, what about this last one? How can I understand this last coefficient in terms of the table?
It's the same thing as the last one, except for instead of using the middle range column, we use the bottom range column.
Absolutely. So I can calculate two probabilities using those two columns of the table. 33 over 33 plus 28, 40 over 40 plus 148. Those are the things that are represented on this graph. Of course, what our model is working on is log odds, which is a transformation of those probabilities.
So you convert those numbers into odds, and then you take the log of those two numbers, and you subtract them, and that should give you 1.47.
Right. Yeah, so if you transform these probabilities into log odds, those two log odds will be things that you can subtract from each other to get that minus 1.47.
So I don't know if I'm doing my math wrong, but I'm doing that math, it's not working out. You're like log of 0.54.
It's natural, but
Oh, natural, right?
Yes. Log basic. Yep. So something that I hope you've seen from this example and some of the preceding examples is that anything you can do with the general linear model, you can also do with the generalized linear model. So I've shown you how to handle a quantitative predictor, that's what we started with, a dichotomous predictor, and a three-level predictor. But I can also do lots of other things. So I can use random orthogonal contrasts. I can do equivalence tests. I've shown you one example of controlling for an extra variable. So we controlled for that second dummy code we're looking at first. I can look at interactions or very complicated interactions. Of course, when you look at complicated interactions, that can be really hard to interpret. But basically, any technique that I could have used for the general linear model, there's going to be some variation of that technique that works pretty similarly in the generalized linear model. So all that infrastructure that you learned about the general linear model should apply pretty well to the generalized linear model. It's one of the benefits of having that framework to think about is that that framework applies in a very general way to a lot of different cases. The one extra complication is that all these techniques work in log oscillator instead of in the land that you might want to understand as the probability land. That does add some extra complications. I think I'm going to hold off. I have one extra idea that I want to talk about, but I think I'll hold off until Wednesday to talk about it because we're running out of time. So on Wednesday, the things that we'll talk about are this one extra complication with the interpretation of logistic regression. I'll also prepare an example graph and write up. Not sure if I'll talk about it in detail in class. I'll pick out time, but I'll have that for you as a reference. And then the last thing that we'll do, this will be the last idea of the last linear model. So I'll talk briefly about other kinds of outcomes that you can utilize using the generalized linear model. Turns out that the generalized linear model applies to all sorts of different kinds of outcomes. You can just use this mathematical bridge that gets you from one way to another. That's a very powerful idea that last two question cases. So all listen.